In this video, we're going to take a look at a full Paper 1 walkthrough for the Cambridge Computer Science 9618 AS level. Now, when you're taking your AS exams in a year, of course this year coming up right around the corner, there are two papers, Paper 1 and Paper 2. Now, Paper 1, you're going to be given an hour and a half to work on that to earn up to 75 marks towards your total overall score. Paper 1 is going to assess sections 1 to 8 of the syllabus content. So that's going to be all the way from binary, all the way to database management and SQL. It is a written paper, so there's not going to be any programming on the computer that you're going to be doing. It's externally assessed, of course, and you're going to answer all the questions. You're not going to be penalized for guessing. So even if you don't know the answer, having something down could help you get 1 or 2 points. It's going to be 50% of your total AS score because your AS exam consists of Paper 1 and Paper 2. It's going to be 25% if you continue with into A level. That's going to be 25% of your score. So if you're going to continue in the A level, you want to do as good as you can on Paper 1 and Paper 2 because it will factor in to your A level score overall. So let's go ahead and dive into the Paper 1 and go through each of these questions. And when we open the first page, we can see that we are being assessed on binary, which is not too hard at all. It should be an easy 3 points to pick up as long as we know what we're doing. So all I'm going to do before I even start calculating this, because you definitely don't want to do this in your head. When you start doing it in your head, it's very easy to make a mistake. So just take the extra seconds and write the values. So we know the first one's going to be 1, second one's going to be 2, third one is 4, 8, 16, 32. Because it's unsigned, I don't need to worry about whatever this leftmost bit is. So I have 32, plus 4 is 36, plus 2 is 38, plus 1 is 39. The next one, convert the binary coded decimal into denary. So what I want to do here is I want to count how many bits we have. We have 8 bits. So I'm going to split it right into 4. And what they want to do, what they want us to do here is calculate this and calculate this. The one on the left is going to represent a digit. I know that's the value of 2. What about the value over here? Well, that's 1, that's 2, that's 4. There is no 8. 4 plus 2 is 6. Plus 1 is 7. So the answer is 27 or 27. Here, convert the 8-bit 2's complement binary integer into denary. The first thing I want to do before I even start doing that is I want to look at this left bit right here. I know the answer is going to be negative. So I'm simply going to put a negative sign there. I want my negative sign to look somewhat neat. Now, when you're doing this, there's 2 ways you can do this. You can do negative 128, because I know that's the value of the far left bit here, and then start adding positive numbers. That's one way to do it. Another way to do it is simply perform 2's complement on it to convert it to a positive, figure out that value, and then just put a negative sign right back in front of it. When you do that, this one, you start from the far right and you make your way to the left. This one stays the same. Everything else gets flipped. So all I'm going to do is perform 2's complement on it. And now I have a number much easier to work with. I know this is the value of 1. There is no 2. There is no 4. There is an 8. There is a 16. 16 plus 8 is 24. 24 plus 1 is 25. And I know this comes out to negative 25. It is that easy. Rather than trying to work with negatives and positives, I know it's a negative. I'm going to bring that negative sign down. I'm going to perform 2's complement on it, figure out what is the positive value, and just write that in front of my negative sign. And just like that, we picked up 3 points of the 75 on our Paper 1 exam. Let's get ready and take a look at the next question. And this question shows binary arithmetic. They want us to do binary subtraction. Now, if you're looking at the syllabus, you may be saying, well, I saw binary addition. What about this subtraction? What do I do here? Well, think of it like this. Let's say you have 4 minus 7. There's another way you can do that. You can do that as 4 plus negative 7. So all we're going to do is perform 2's complement on this number right here. So I start from the right, working my way left. I keep all zeros the same until I encounter the first one. Here's my first one. It stays the same. I'm going to change this 0 to a 1, this 1 to a 0, this 0 to a 1, this 1 to a 0, this 1 to a 0, this 1 to a 0, and this 0 to a 1. All I need to do now is make this a plus sign, and now it becomes much easier. When you're doing addition, remember there are a couple ways this can go. You can get 0 plus 0, that's going to result in a 0. You can do 0 plus 1, that's going to result in a 1. You can do 1 plus 0, that also results in a 1. You can do 1 plus 1, which results in a 1, 0. Now this 1 will get carried to the next column, and there's one more, which is 1 plus 1 plus 1. Because if this one gets carried over and you have two ones that you're adding, then you're going to wind up with 1, 1. Why is this the case? Well, what is 1, 0 in binary? That is equal to 2. What's 1 plus 1? 2. Here we have 1 plus 1 plus 1. That comes out to 3. What is this number in binary? It's 3. So that's why we do that. So here we have 1 plus 1. I look over here, I see that results in a 0, and I carry the 1. That results in a 1, I carry the 1. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 0 is 1. 0 plus 0 is 0. 1 plus 1 is 0. Carry the 1. Now there's nowhere for that 1 to go at all. So what we can do is, this is our answer right here. So we have 0, 0. Then we have 3 ones, 1, 2, 3, and then 2 more ones right here, 1, 1. So our answer is, if I write the values, 16, 32, so that is 48, 56, 56 plus 4 is 60, plus 2 is 62. Our answer is 62. Now, they didn't ask us to perform it into denary. It says, just perform it, and this is our answer that we have right here. If you don't want to get rid of this 1, I would strongly recommend that you show it off to the side here. I would either put it here, or you can bring it down here and put it in parentheses. Do not bring it down here, because if you bring it down here, you're putting it into a column that doesn't exist. So, just show it off to the side. If you want to bring it down the same line, you can. Just put it in parentheses to show that it's going to carry over. But that is the answer to the question, and that's how you're going to do subtraction. Most likely, it's going to ask you subtraction on the paper 1 exam, but let's go ahead. Let's move on to the next question on the paper 1 exam and pick up even more points. Question 1C is going to ask about ASCII code and Unicode character sets. Not a problem. This is simply assessing, do you know what ASCII code is? And do you know what Unicode is? If you know what ASCII code and Unicode are, you're equipped to answer this question. If not, it's very easy to recognize the difference between them. And we can do that right now. So both of these use a unique binary code to represent a character. Now, Unicode also contains all of the ASCII code characters. ASCII code has up to 8 bits. Unicode has up to 32 bits per character. So ASCII code takes up less space than Unicode. So if I'm going to represent any character that shows up on the ASCII code, I want to use ASCII code for that. I don't want to use Unicode because that's going to take up more space. However, ASCII code is for a single language, and that's going to be English. I can find all the English characters on the ASCII code chart. There's some characters, like, say, Mandarin, for example, I cannot find on the ASCII code chart. I would need to use Unicode, and that's because Unicode includes characters for other languages. Now, when I'm talking about characters, I mean single letters or other single character representations. That could be for a number or any letter or character in a language. Unicode also has far more characters than ASCII code characters do, and that's the difference between Unicode and ASCII code. So now we've picked up a total of 8 points, more than 10% of the total points we can earn. Let's take a look at the next question. And here they're asking us about sound, and it says, state what is meant by the sampling rate. That's simply a definition. It's the number of samples taken per second. We have an analog file that we want to convert to a digital file. When we do that, we take a sampling rate, and that's the amount of samples taken per second. You may see in an MP3 file or another audio file, they may say 44.1 kilohertz because it's measured in hertz. Each hertz is one sample per second. So if it's 44.1 kilohertz, that means there are 44,100 samples taken per second. So that's what that means. Explain the effect of increasing the sampling resolution on the sound file. Well, if I'm increasing the sampling resolution, I know there are two things that happen right away. This one's worth 2 points, and we'll go over everything that you can list. Well, I know that it's going to increase the quality of the file. Now, the one thing I want to do on my Cambridge exam is make sure I don't get marked NE by my examiner, which means not enough. I want to, explain what I mean by increasing the quality of the file. I'm saying it's closer to the original analog source, whatever that may be. There's also a larger range of values as more bits are used to represent the sample. Now, when I say larger range of values, that means when the pitch gets really high or the pitch gets very low, or there's a gradual crescendo or decrescendo, I'm able to represent that very smooth because I have more bits to be used. Now, the file size, though, when I increase the sampling resolution, yes, I'm increasing the quality of the file, but that's also going to increase the file size because the sample resolution has increased. What does that mean? More bits are used to represent the file. So if I say I increase the quality of the file, which also increases file size, I'm good to go. You do not need to write more than two things because we're doing a paper one walkthrough. I want to go ahead and go over everything that they would that they would accept. I've been teaching this for a long time, so I know what they're going to accept, what they're not going to accept, and we want to remove any possibility of getting marked NE and make sure we're getting all 75 points. Let's take a look at the next question, which involves matching. All right, we're on question number 2, which means a new topic. Draw one line from each security feature to its most appropriate description. Firewall. At your school, and probably most likely your home computer, you have a firewall. But what do firewalls do? Well, they check incoming information. They check the bits that are coming in, which make up data. It's checking to make sure that it's allowed into your computer. It also checks data going out from your computer because it's checking both bits of data coming in and out. It accepts or rejects incoming and outgoing packets, which are bits of data based on criteria. The next one is farming. Now, another word you want to know with farming is phishing. No, they are not the same thing. Phishing involves using email. They're trying to get you to divulge your identification, your login identification, credit card information, or whatever. We've all seen these phishing emails where a long-lost cousin in Africa emails you, and the next thing you know, you got $10 million worth of gold coming your way. I've gotten that offer numerous times. There must be tons of relatives that I don't know about. Farming, on the other hand, doesn't use email. What it uses is uses websites. So what it does is it poisons the DNS server, and then when you go to a website, you're redirected to a website that looks authentic. When you type in your user login information, it just got sent to somebody. So they're trying to steal your information by using a fake website. So that redirects the user to a fake website. Antivirus software, that is an example of utility software, and that's making sure that, hey, we have no malware on our system. So it scans the files on the hard drive for malicious software. Then we have encryption. Now, there are two boxes left here. Converts data to an alternative form or verifies the authenticity of data. Encryption doesn't verify anything. Encryption converts the data to an alternative form. That way, if someone intercepts it, they're less likely to crack it. Now, you may be saying, well, what about that last box here? Well, Cambridge doesn't like their people who are testing to use the process of elimination. So if you have one or two boxes left over, nothing to worry about. It is intended to be that way. All right, so that's going to be it for this question. Let's move on to the next one and pick up even more points on our paper 1 exam. All right, the logic gate. So you definitely want this to show up. What's interesting about this one is it only involves 3 inputs, A, B, and C. You want to be able to handle up to 5 inputs, A, B, C, D, and E. I have seen a couple exams where there are 5 inputs, but if you can understand 3, you can understand 4, and you can understand 5. What you have to know is simply the rules and how these logic gates are drawn. Once you know how they're drawn, you're good to go. So let's go ahead and let's handle the inside parentheses first. So we have not A. So I'm going to go ahead. I'm going to draw my triangle. And what I want to do is put an open circle so I know it. So my examiner knows it's my not gate. So I have not A and. So I'm going to go ahead and draw my and symbol, which looks like a D. My students call it a spaceship. I call it an AND gate because that's what it is. And it says not B. So I'm going to draw my triangle again. I'm going to put this little open circle. That's an inverter. So what it does is it inverts the value of B. I'm going to draw my line. So that takes care of all this. That whole part is done. Then it says or. Well, let me go ahead and factor these right here or handle these. So I have not B. Now, I want to branch off from this part right here. I don't want to do it before the not gate because that is simply B. But this says, hey, we're doing not B. So I want to branch off right here. And I can do that and show Cambridge that I'm branching. I also need to do my not C. So I'm going to go ahead and do that. I'm going to show that inverter there, and it wants me to put it through an AND gate. So I'm going to draw my other AND gate here. Actually, I want to make it bigger. Now, on the exam, when you're drawing your AND gates, make sure it's not, don't confuse them with a OR gate. You want to make sure that it's clearly seen that it's an AND gate. So I'm going to draw my not B, my not C. Now, I need to OR these together. Now, don't forget about this not. We're gonna do that in a second. What I want to do is I want to have not, and you'll notice this OR is inside the first set of parentheses here. The second set is to handle each of these. I need to OR these values together. So I'm going to draw my OR gate here. And then what I'm going to do is I'm going to bring that value from both AND gates because those results are ORed together. Now that takes care of all my parentheses. The last thing I have is this not on the outside. I draw another not gate. I'm going to show that open circle, make sure it's an open circle, and then connect it and then just draw it out to this X. And just like that, we have picked up 2 points. Let's take a look at the logic or the truth table that they're also most likely going to assess you on when you see a logic gate. Complete the truth table for the logic expression. Okay, the first thing I want to do is simplify this down. In AS, you do not have to know how to do Boolean algebra. You don't need to know Boolean algebra to factor out this not here, which is actually going to make this problem a lot easier to solve. So let's go ahead and distribute this. What is not A? Well, if it's not A, well, then it must be A. So I'm going to write A. Just so you know, this working space is never graded. So it really doesn't matter what you write in here. It's not going to be graded. The next thing you need to know is, okay, what about this and? We'll come back to this in just a moment. So what about not B? Well, if it's not B, it must be B. Now, what about this symbol here? What about this and? Well, if it's not and, it's got to be or. So now I have A or B. Well, if it's not or, it must be and. So I can have A or B, and I can have, well, we still got to distribute this not all the way over here. Well, what's not B? That's B. Here we have the and. Well, what is not and? That's or. And what is not C? That's C. So now I have something much easier to work with and a simple way to give me 2 points rather than trying to give myself a headache. So in the first one, I need A and B. I need A and C. So I can have one of those. I can have A and B because of the and here. I can have A and C. The other option is I can have B and B, which is just B, or I can have B and C. Those are the options, and as long as I follow those, I will get all the points filled in. So I know with an and, both of these must result in a 1. With the or, only one of these have to, or at least one of these have to result in a 1. If you're not familiar with the XOR gate, that means only one of these can result in a 1, not both. But we have and an or here because we made it a lot easier to work with. By writing out all these possibilities, we're good to go. So I can see in the first one, I don't have AB, AC, or BC, so that's a 0. And the next one, I just have C. That doesn't work. That's not an option. Now the next one, I do have B. That's going to work. And you may be saying, well, I don't have B. Well, if it's B and B, that's going to simplify to just B. You can't have B and B. That's just simply B. Now, B and C. That was an option because here I have B and C. Here I have just A all by itself. That's not an option up here. So I put a 0 here. Here we have A and C. And we can see that was an option right here. So I put my 1. The next one is A and B. I have that option right here. And the last one is where all 3 of them. So all 3 of them, well, if I have A and B, then I also, that works because it says A or B and C. So I can have A and B as 1. That results in a 1. And I got to have B or C. Well, if I have C here, that results in a 1. Now, the way this is going to be graded, it's going to be, you got to get these 4 correct, and you have to get these 4 correct. So you can't just put in 0, 1, 0, 1, 0, 1, 0, 1, or all zeros and all ones, hoping that you'll pick up points that way. That doesn't work. And like we discussed earlier, Cambridge wants to make sure that you're not able to get points by guessing or to use the process of elimination. Let's go ahead and move on to the next question. All right, making our way through this type of question, which is on a, when I see a relational database, this is on almost every paper 1 exam. You definitely want to know how relational databases work, which means you need to know primary keys, you need to know foreign keys, you need to know first normal form, second normal form, third normal form. These are worth a lot of points, and you want to make sure that you definitely get these easy points. So if you're saying, well, I'm not very familiar with it, don't worry. You still have plenty of time to become extremely familiar with it. I also have a video that walks you through how to do it. So let's take a look at this question though. A photographer creates a relational database to store data about photographs taken at birthday parties. The database, photographs, stores the details of the customer, the party, the photographs taken, and the cameras that are used. The photographer has several cameras that are used for taking the photographs at the parties. I don't know what else you would do with cameras other than take photographs. Each camera has a specific lens type, for example, XY32Z, and a lighting type, for example, F1672. Data about each photograph is stored in the database, including the party at which it was taken, the time it was taken, and the camera that was used. The database has these 4 tables. Okay, the first thing I need to know is that when I have something underlined, that's what we call the primary key. Each primary key can show up in a separate table as what is called a foreign key. So the first thing I want to do is identify all the primary keys. Once I have all the primary keys identified, it makes this entity relationship diagram, which is worth 3 points, a lot easier to fill out. So here is my customer table. So right here are the name of my tables here. That's got to be one of the worst boxes I've ever drawn, but that's okay. So customer, what does it have? It has customer ID. First name, last name, telephone. That doesn't matter right now. Customer ID, I want to ask myself, okay, let's start with party. Does customer ID appear in party? Well, I look at my party table, I have party ID, I have customer ID. It shows up in this table as what we call a foreign key. Because I have a primary key in customer and a foreign key in party, which are the same values, they are related. That's what it means by relational database. How many times can customer ID show up inside my table customer? Well, because it's a primary key, it can only show up one time. Now, I need to draw my relationship with party. Is customer ID a primary key in the table party? No, it's not. It can show up many times. So I draw a one-to-many relationship. So that takes care of customer and party. Let's see if customer shows up in camera data. So I look at my camera data table. I see camera ID, lens type, lighting type. I don't see customer ID, so there's nothing to draw between these two. Let's check photo data. So I see customer ID and customer. I check photo data. Photo ID, party ID, time taken, camera ID. I don't see customer ID as a foreign key at all, so the only table that customer is related to is party. Let's do the party. Party has a party ID. Well, we know it's not in customer because we already checked that. Let's check photo data, which is this table right here. We see photo ID, party ID. There's my foreign key right there. So I know party and photo data are connected together. So I'm going to draw that one-to-many relationship. But why? Party ID is my primary key. I can only have that value one time. But when I look down here at photo data, it's a foreign key. I can have that value multiple times. So that is a one-to-many relationship. Let's see if there's any relation between party and camera data. Party has that party ID. When I look at camera data, I see camera ID, lens type, lighting type. I don't see my foreign key, so I know they're not related. Let's do photo data and camera data. So photo data has photo ID. That doesn't show up in down here in camera data. I have camera ID, lens type, lighting type. Now, let's check the last one, camera data. Let's see if camera data is related to customer. Camera data has the primary key, camera ID. I see in customer, it has customer ID, first name, last name, telephone. No foreign key, so I know camera is not related to customer. Is camera data related to party? Well, I have camera ID. Inside the party, I have party ID, customer ID, party date, start time. I don't have camera ID. Well, there's only one table left, photo data. So I have camera ID. I'm checking photo data. I have photo ID, party ID, time taken, camera ID. There's my foreign key for the camera data table. So now these are related through these. Well, how many times can camera ID show up inside my camera table? It can show up one time because it is a primary key. So this is the symbol for one, just a single line. How many times can it show up in photo data? It can show up many times. So I draw my mini symbol, which my students like to call the crow's foot. And just like that, I've picked up 3 points for this question. Let's move on to the next one. All right, for this question, this one can be a little tricky. You'll notice it is 3 points here. And you may be saying, well, third normal form, I know there's 2 rules. It's got to be in second normal form, and there can be no transitive dependencies. But there's no other rule for third normal form. Well, in order to get into second normal form, you got to be in first normal form. So what does 1 in F mean? Well, 1 in F means is that there are no repeating groups, and we want to call it by its actual name. There are no repeating columns. And what are those columns? Those are attributes. So there are no repeating attributes whatsoever. There's also, when we get the second normal form, there are no partial dependencies. And we need to explain what that means, because remember, we don't want to wind up with an NE on our paper. So we want to say everything is dependent upon the primary key. And then sometimes in second normal form, we have a composite key. Primary key, and we're going to say and slash or the composite key. Because if we have a composite key, that is our primary key. It's just composed of more than one attribute. Now, now I'm not going to label on my paper that this is 1NF, this is 2NF. I don't want to do that. But I may want to make a note to myself somewhere off, maybe up here is once it's in 1NF, I can get to 2NF. Once it's in 2NF, I can get to 3NF. And what is the rule for 3NF? The rule for 3NF is there are no transitive, and that's the word you want to use. You want to use the word transitive. That shows that you really know your stuff, dependencies. And that's when one item is related to the primary key through another item. So this one isn't solely dependent upon the primary key. It's dependent upon the primary key through another attribute that is not a primary key. That's what we mean by transitive dependencies. So really knowing your relational database allows you to pick up 6 points, the previous question and this question, easily by reviewing topic 8 on your looking through your notes or through the book or watching videos, whether they're my videos or somebody else's. I mean, I hope you're watching mine, but what I'm more concerned about is you're getting all your points. So, use what information is available to you. But picking up 6 out of 75 points, I mean, that's almost 10% of the points you can earn. So you definitely want to be able to pick up those 6 points, and you should be able to. But let's go ahead and take a look at the next question. Okay, so here they give us a photo data table, so we can actually see it populated with some data. It says state what is meant by a tuple. So the first thing I want to do is go over the difference between tuples and attributes. So you may want to add this to your notes. You wouldn't need to do this on the exam. They're asking about tuples, not attributes. Attributes are simply your columns. Tuples, on the other hand, are your rows. And if you know that, if they ask you to identify a tuple or identify an attribute, and attributes are columns and tuples are rows, you're able to pick up those points. So I see there are 1, 2, 3, 4, there are 5 tuples, there are 1, 2, 3, 4 attributes, and photo ID is going to be most likely my primary key. But they're not asking about that here. Usually when they give you a table, they're going to be asking an SQL question, so I'm sure that is coming up. So state what is meant by a tuple. It's one row, and you don't want to put rows in a table because that is the data that's in a table. A tuple is simply one row in the table. So if they say identify the third tuple, then you would need to identify the third row. Here they say, give an example. We'll use the third row. We'll use this one right here. So we'll say photo ID, and I don't want to abbreviate. I don't want to do PID. I definitely don't want to do that. PID is not even in this table, and we don't want to get marked in E for not enough. I have party ID. So all I'm going to do is pick any row I want, and I'm simply going to put those values. And the reason I want to put those values is because if I just do photo ID, party ID, time taken, camera ID, they're going to say those are attributes, and they're going to mark it wrong. The party ID was BC08. The time taken is 9:01. And the last one is the camera ID. And I'm going to put the camera ID for that one, which is CAN-01. I imagine that represents Canon and the NIK Nikon. But anyway, that's how we pick up those 2 points. Make sure you know the difference between attributes and tuples. Let's go ahead and move on to the next question, which is most likely going to be SQL. So let's take a look and see. Complete the structured query language, so SQL script, to display the total number of photographs. Okay, the first thing I want to do is start figuring out what they're asking me here. Total number, so I know that's going to be the command count. So I know I'm going to need to use that of photographs that have been taken using a camera with a camera ID starting with can. Starting with can, I know I'm going to need to use the like command. I'm also going to need to use a star symbol after can, and total number of photographs that have been taken using a camera with a camera ID. So I'm looking with the camera ID, and there's one table that has the camera ID. Also notice this is 4C part 2, and they're talking about this table right here. So it says table shows some sample data for the photo data table, and because that was 4C, we're able to know that they're referring to this table right here. So the first thing I want to do is I want to select what? Well, I want to count of all the photographs that have been taken. Now, how do I count? It says the photographs that have been taken using a camera with the camera ID. So I'm counting. So what am I counting here? Well, starting with taken using a camera ID. So it says count the total number of photographs. So am I counting how many attributes there are with a camera ID, or am I counting the number of photos? Well, it says display the total number of photographs. So each one has a photo ID. So I'm going to be counting how many photo IDs there are. And in that example of that table, there's 5. So I'm going to do photo ID. So right here, I'm selecting count. What am I counting? I'm counting photo ID. I'm selecting a attribute or a column here. From what table? From where? What table in the database? Well, I'm doing it from this table right here. What was this table called? It was called photo data, and that's why I displayed that here, because we need to know the name of the table. So anytime you see from, you're going to put a name. Photo, I'm going to put it in all caps, just like they have. Data, and data is in all caps too. And then it says where camera ID like, so they've given me like, that's okay. They've also given me a semicolon. The semicolon goes at the end of a command. This is one whole command here, and it says starting with can. So all I need to do here is going to use my single quotes. I'm going to put can. Then it needs to be anything that can show up after CAN, which is -02, -01, whatever it may be. So all I'm going to do is simply put an asterisk here, and that means anything that starts with CAN, we're going to print out, and they've already given me my semicolon, and just like that, I picked up 4 points. I spent a couple years ago, I asked my students, what do you want to review? It was about 2 weeks before the test, and they said, we really, really want to review SQL. I said, all right, that most likely is going to show up on the exam. We spent 2 weeks, several hours, really drilling through SQL. They were ready to get, no matter how many points it was worth, they were ready. When they came back from their exam, I asked them, how did it go? And the very first thing they said to me was, there wasn't any SQL at all. I said, not a single one. They said, all that was on there was creating the database. They said it was worth 1 point. There was one question on SQL. You want to be ready for SQL just in case you have a question like this, which is 4 points. But if you can do the basics of SQL, you'll be able to answer these questions. If you have any questions, please post a comment below. But in the meantime, we're going to move on to that next question. All right, write an SQL script to include 2 new fields in camera data to store the number of photographs. I'm going to have number of photographs currently on the camera and the date the camera was last used. All right, so that's what we're doing. So they tell us what table we want to update. We want to add 2 new attributes or fields into our table. So the first thing I want to do is I want to identify the table we are changing, as well as give that SQL command. When I want to change a table, I use alter table. Now, when I do alter table, our commands are always going to be in uppercase letters. What table am I altering. I'm altering camera data. Now, when I alter a table, I can add a column, I can drop a column, I can also add a primary key and a foreign key. And here, all we're doing is adding 2 new columns. So I'm going to add, what am I adding? I want to give myself a column heading or column name. So it says number of photographs. So I'll do num. I'll do num of photos. Now I need to identify what data type that's going to be. That's going to be an integer. But that's not the only thing I'm adding. Because I'm adding more than one thing, I can keep it on the same line here and date the camera was last used. So I'll say it was last used. What is that data type? That data type is a date. I am done altering my table. I put a semicolon and I am done. And I just picked up 3 points there. One for altering the table. I'm adding a number of photos as an integer and my last used as a date. So with that, we're ready to move on to the next question. All right, so 5A and B part 1 state what is meant by the stored program concept in the von Neumann model of a computer system. So one of the best tools that you can use is what is known as the little man computer. This will really help you understand the von Neumann model or the stored program concept. It really does a wonderful job of doing that. It'll allow you to see what the program counter does. The index register and status register, that's not on the little man computer model. However, you can become familiar with those by doing trace tables. But if becoming familiar with von Neumann, little man computer is really a great tool to use because it illustrates the stored program concept. And what is the program? The stored program concept, that's going to be where the instructions and data for the program are both stored, and they're both stored on the RAM or the main memory. We'll say main memory just so it looks a little more impressive, are both stored on the main memory. There we go. That's what it is. And if you've ever used the little man computer, you will know that it's the main memory where we have to store data. We have to fetch instructions. There's a current instruction register. There's a memory address register. There are the buses, but we'll get to all that. The program counter. The program counter stores the address. And it stores the address of the next instruction, not the current instruction we're on, because as soon as we get that, it increments. So it stores the next instruction to be fetched. So that's the first part of the fetch, decode, execute cycle, also known as the fetch, execute cycle, to be fetched. Now, the index register, that is shown when you do a trace table. And what this is, it holds a value that is added on to an address to get a new address. And you'll see this when you do, you'll see like LIX, you'll see LDX, I think is another one. You'll see all those. That's messing with the index register. Now, your status register, it stores flags. And there's 3 things it's going to store flags from. And it's going to be from events, and there are 3 types of events: from the results of adding, subtracting, arithmetic. So we can say arithmetic. It also does logical operations or logic operations. Those are your and, ors, your nots. So we'll say logic operations. And the last thing a status register will do is it will handle interrupts. So handle, well, actually it doesn't handle interrupts. It stores flags for interrupts. Whether a interrupt has been handled or not by the interrupt service routine. All right, so that's 5A and B1. Let's go ahead and move on to the next part of this exam. Tick one box in each row to identify the system bus used by each CPU component. There are 3 buses: the data bus, address bus, and the control bus. The system clock. These are the pulses given by the computer, and when the pulses are done, it sends a signal. So that is the control bus. It says, hey, we're going to synchronize everything. It's going to be on the system clock, which is going to send out a pulse, and that's going to activate everything. The control bus decides what to do with the data, whether we're going to read or write to the RAM. The memory address register. The memory address register works with the address bus. Now, when you're looking at the memory address register, you'll see if you're doing register transfer notation, you'll see this. And if you see this, register transfer notation doesn't appear on this exam, but if it appears on another one, you need to know the difference between these. This means the address. This means whatever is inside the memory address register is the address. If you see double brackets, and that's a bracket, not a parentheses. If you see a set of double brackets, that means the contents or the data at the address. So just something I want to point out there. That way you can understand the difference. And this is part of what we call register transfer notation, which doesn't make an appearance on this exam, but it could. Okay, so the CU, the control unit, what does that do? Well, that synchronizes on each clock pulse actions of the other components. That are parts, let's see here, that are parts, that is the worst looking that I've ever seen. My handwriting is not that nice to begin with. That are part of the CPU. The other thing it does is it manages execution of a program in sequential order. Well, it's actually instructions because we're talking about the main memory. So the instructions in sequential order. And all that means is we're going to follow a sequence of steps. You can also jump around. There's different jump commands that can happen. And it controls communication. You only need to list 2, but this will be I'm pretty sure everything, and it controls communication between the CPU components. And that is part of the, if you go to the Little Man computer and spend some time with it, if you need a video, post a comment and let me know. But if you spend some time with the Little Man computer, you'll see how it controls communication between all the CPU components, all the different registers and what they do. All right, so with that, let's move on to the next part, C and D. Describe the purpose of an interrupt in a computer system. And what that does is it sends a signal to another device our program running. And when we have a program running, we call that a process, or program that is running. And when we have an interrupt, we're grabbing the attention, or we're trying to get the processor to do something. So the processor will handle that interrupt. The instructions go on to the processor to handle the interrupt. The processor will handle the interrupt. Now, the interrupt isn't on the processor, or to handle the interrupt is not automatically on the processor. That is loaded up by the interrupt service routine. So the processor will handle the interrupt by executing instructions. Now, Cambridge abbreviates it as the ISR, so we can do the same. The processor will handle the interrupt by executing instructions of the interrupt service routine. So that will give us our points there. Don't know what happened to my pin there, but that's okay. All right. Identify two causes of an interrupt. If you've been doing any programming, which you have because you're in AS, you have had software interrupts. Maybe sometimes you've had to, maybe you've done dividing by 0. When you divide by 0 or divide by a null value, that's going to cause your program to crash. So dividing by 0, 0 is not a null value. That's just not allowed. Dividing by something that is not a value at all, nothing there, that's a null value. Going outside the bounds of an array. So going outside the bounds of an array. If you run a loop that is indefinite, eventually you're going to run out of memory space. You'll see it'll say stack overflow exception. If you've had a loop run forever, where it's adding numbers, adding one to one, eventually it's going to get a stack overflow. It's not able to store any more data. All right, so that's going to wrap up number 5. Let's go ahead and move on to number 6. Making good time here, almost done. If you haven't taken a break, now would be a good time to do so. Just take a break, get a drink, and just, relax for a few minutes, and then come back and be ready to resume. All right, when you get to a question like this, it can be really overwhelming, but this table on the previous page, that is the key. One of the worst things you can do is not prepare for this question. If you go into the exam saying, you know what, I don't need to worry about those trace tables, I'll figure it out when I get there. That is not how you prepare for a challenging exam. Being familiar with some of these commands make it so much easier to do. So let's go ahead and start. 77. That goes on row 2. Why does it not go in row 1? Because we're not loading these values in these addresses. What am I doing at 77? I'm doing LDR number 0. Immediate addressing. Load the number to the accumulator. So it's saying, hey, load 0 to the accumulator. 77 is done. I'm going to put a little check mark. The next line I'm going to run is 78. What am I doing at 78? LDX 110. I'll look at LDX. Form the address from the address 110 plus the contents of the index register. Copy it to the accumulator. Okay, 110 plus 0 is 110. What's the contents at 110? That is 66. We put that inside the accumulator. The next address is 79. It says compare number 35. This means compare the contents of the accumulator with number n. And there it is right there, and that's what it says. So let's compare 35 and 66. Are they the same number? No, they're not. Did 79 run? Yes, it did. Just because the computer compared them, so now we move on to line 80. Looking at 80, jump if equal. Following a compare instruction, jump to the address if the compare was true. It says jump to 92. Well, only if it was true. It wasn't true. So I moved to the next line, 81. 81 says add 100. If you notice, there are two adds. Add the address and add number in. Add the contents of the given address to the accumulator. It wants me to add address 100. What's in 100? 0. I can do 100 plus 0. That's 66. Put a little check mark. 82. 82 says store 101, and it's going to be store the contents of the accumulator. And this is why you want to be familiar with it. So I'm going to go to 101. I'm going to write 66. Beautiful. The next, put a little check mark here. 83. 83 is LDM number 1. Media addressing, load the number into the accumulator. The number it gave me was 1. Then I run, put a little check mark here, 84. I'm adding the contents of address 100 to the accumulator. What's in 100? 0. What's the contents of my accumulator? 1. 1 plus 0 is 1. So that's what I'm going to do here. Now, something I want to do is go back and update this 101 value, because right over here, I need to update it so it says 66. Because if I look back over here and it says 0, that could, cost me quite a bit of points. All right, 84 is done. The next thing I'm doing is 85. So we're on address 85. It says store what? The accumulator and the address 100. So I do that. 85 is done. The next line I do is 86. It says INC, which is increment the index register. So if you see INC, it says the register. So add 1 to the accumulator or the index register. It tells me IX. So that's what I'm going to do. Right now in the index register, nothing is there. So that has a value of 0. So that is going to be a value of 1. So I want to make sure to do that. You know what? It was 0. I put this in the wrong spot. Let's look at LDR. LDR says load the number into the index register. So what I'm going to do, because I just made that mistake, I'm just going to put a strike through, let Cambridge know, hey, I made a mistake. Luckily, we caught that early enough. 87 is LDX 110. And remember, LDX is index addressing, from the address plus the contents of the index register. So 110 plus the index register, which is 1, that's 111. Yep, 110 plus 1 is 111. That is 65. So that's what I'm going to do on line 87. I'm going to load up 65. 87 is done. I'm going to go to 88. 88 says compare 65 and number 35. They're not equal. So I move to the next line, 89, JPN, which means jump if not equal. Following a compare instruction, jump to address if the compare was false. 65 is not equal to 35, so that is false. So it tells me to jump to line 81. Check these off. So what's the next address I go to after 89? I go to 81. So now I'm going to keep my check marks on the right hand side so I can keep track of them. So when I jump to 81, not 77, it says add the contents of address 100. 65 was the last thing in my accumulator. What's that address 100? That is 1. Need to update these over here, or you need to look on your paper over here. Either way, whatever you want to do. So what is 65 plus 1? That is 66. So I move to line 82. 82 says store 101. What am I storing? I'm storing the address of the accumulator. So 82 says store in 101. So 101 becomes 66. I'm just going to draw that. 66 is already there. That's fine. I'm not going to update it over here because 101 is already there. The next thing is load number 1 into the accumulator. So I'm going to load number 1. Then I have 84. 84 says store that number inside address 100. So I'm going to go to address 100. I'm going to put a 1. And right over here, we see it's already a 1. So it's just 1 is being overwritten with 1. So that was line 84. I just did that. Then I did line 85. So line 84 Nope, I didn't do that. Okay, so let's figure out. I skipped a line. And this is why you want to go nice and slow. This is a prime example. Okay, let's do 84 because something doesn't look right. I shouldn't be getting the same number here. So 83, we load up number 1. Oh, we're going to add the contents of the accumulator with 100. Address 100 is 1. 1 plus 1 is 2. Okay, now we are storing it, which is 85. So you want to go nice and slow there. That's a prime. I just did a prime example of not being meticulous. So 85, we're going to store in 100. So line 85, we're storing the contents of the accumulator 2 into address 100. 85 is done. 86, we're going to increment the index register. My index register was 1. It is now 2. Go to 87. 87 says, okay, add the contents of the index register to 110. That is 112. Load that into the accumulator. So at 87, I'm going to load up value 35, and that's going to give us to 88. We're going to have extra lines here. That's okay. In 88, what I'm doing is I'm comparing number 30 or the accumulator 35 to the number 35. They are the same. Now, the next line that runs is 89, which is JPN. However, it does not execute. So let me explain what I mean by that. The computer will read JPN or address 89. It will read JPN 81. But because they are equal, we are not going to jump to line 81. The next address we're going to go to is address 90. Address 90 says, load up address 100. What's in address 100? That's the value of 2. So I'm going to put 2 into my accumulator. The next thing I want to do is add number 48. So this is the second add that we look at. Add number 48 to the accumulator. 48 plus 2, that is 50. So 50 is in my accumulator. So I just keep going down the instructions. The next one is 92. That says output. Okay, so I'm going to output 50. Outputting 50 is the character 2. So that's line 92 is output. So make sure I'm on that row. I go to output. I put a 2 there. And then 93 runs and we're done because 93 says end. I don't update any rows. So it looks like we have 3 rows left over and that is fine, but that is how we pick up the 4 marks. Now, I did make a simple mistake there as you're going through. So always double check where you're at, because if you start going and you start getting too far ahead, you may have to backpedal several ways. If you do make a mistake like I did here, just put a dash through it. Just put a single strike through it and they will see it, but they will not grade it. Let's go ahead and move on to the next question. The following instructions are repeated for your reference. So they have LDD and STO, and that's all we see here. State the purpose of this part of an assembly language program. So they load address 100 into the accumulator. They store it in 165. So we're adding something to the accumulator, then it gets stored. So to the accumulator, then stored. And I'm just making little notes to myself here. Then we load up address 101. We're going to store that in 100. Then we load 165. Okay. So what this is doing is it's loading up address 100. It's storing it in address 165. Then we're updating or uploading address 101, storing it in address 100, which is going to overwrite what was originally there. And then we're loading up 165, which we stored to store in 101. So what this is doing is it is switching the contents or the data. I'm going to use contents because that's what they used. That's what they used here. Switching the contents of address, and that's these 2 lines right here, or these 3 lines. How I know that is 100 and 101. And this store right here is so we don't lose what's in address 100. When we load 100, and we store it in 165, it allows us to access it again. So switching the contents of address 100 and 101. And just like that, I pick up a point. Let's go ahead and we're getting closer to the end. So let's go ahead and move on and wrap up this test. All right, so in this one, it says the current contents of the accumulator are, and they give us the contents, show the results after the execution. So all I'm gonna do is I'm gonna XOR this binary number with the contents here. So what I'm gonna do to make it easy, so I'm just gonna write the contents right up here. And basically they're asking, do you know the rules for XOR? And when the rules for XOR are only one of them cannot be true, not both. So in this first one, both of them are true. That's not allowed. That's a 0. In the next one, both of them are true. That's not allowed. In the third one, it doesn't matter if you go left or right. It doesn't matter for this one. 1 XORed with 0. That's a 1. 1 XORed with 0. That's a 1. Both of them are 1. That's not allowed. That's a 0. Both of them are 0. That's a 0. Both of them are 0. That's a 0. Here, only one of them are true. That is allowed. That is a 1. So that's our answer for that one. And it's basically asking, hey, do you know the rules for XOR? All right, the next one, they want us to AND. So I'm just going to write the binary number here. So let's see here. Yep, 4. Just drawing that line there to separate it so it's a little easier to read. Do you know the rules for AND? The rules for AND, both of them must be true. So it says bitwise AND operation of the contents with the binary number in. 0 and 1, they're both not true. That's a 0. 0, both of them are 0. That results in a 0. Both of them are 0. That results in a 0. Both of these are 1. That results in a 1. 1 and 0, not allowed. 1 and 0, not allowed. 1 and 1, yep. That'll work. So now they're going to ask us about OR, and we can easily do that. All I'm going to do is write that new binary number right above here. And we're going to do OR. With OR, at least one has to be true. It doesn't one or the other. That's XOR. OR is simply at least one. So 0, 1. We have at least 1. 0, 1, we have at least 1. 1 or 0, we have at least 1. 1 or 0, we have at least 1. So as long as we have at least one value being 1, that's going to result in this answer. And they're going to give us a total of 4 points for that. They had us do XOR, they had us do AND, they had us do OR, and then they want us to do what we call a logical shift. This does not mean left shift right. It means logical shift right 2 places. So what I'm going to do is I'm just going to shift it to the right. It does tell us that zeros are introduced on the left-hand end. You need to know that just in case they decide not to tell us that. If you leave these blank, that's going to be incorrect. So all we're going to do is move this 1 over 2 places. So I'm going to move that 1. That takes care of that. Followed by the 0. Because once I identify this first number, we're good. Because all I got to do is write the rest of it. So we got the 0. We have this next 0. We have a 1. We have a 0. We have a 0. And we put zeros on the end. Just like that, we are done. What about these values? We ain't got room for them. They just get missed. They're gone. We don't have room down here in our 8 bits to store them, so they disappear. All right, let's go ahead and move on to the next part of the question. We're getting closer to the end, so hang in there. All right, so this is for a 2-pass assembler, and all we have to do is says tick 1 or more boxes. So that's kind of a hint there. Comment removal. When you put comments in your code, documentation, that's like in VB, that's done with a single apostrophe. In Java, it's 2 forward slashes. In Python, it's a hashtag, $. Those comments are removed. That happens in the first pass. Now it says read the assembly language program 1 line at a time. Well, it does that on the first pass to identify any jump references that may happen. It happens in the second pass because those reference addresses are replaced with absolute addresses, generates the object code that's in the second pass, and then it checks the opcode in the instruction set only in the first pass to make sure that it's actually there. So that wraps up all of number 6. All we have left is number 7, and we'll be done. State 2 benefits to a programmer of using dynamic link library files. And I thought there were only 7 questions. Turns out there's actually 9, but they're very short. They won't take long to get through. 2 benefits to a programmer using dynamic link library. Well, the file size is small. See here, small because, and the reason that is because the DLL file is not part of the program. It's called only when it is needed. So it's not part of the program. It's called only when it's needed. Now it does move a little slower because it's being called. The other thing that, there's lots of things you can do here. There's no need to recompile the program when changes are made to the DLL, so you can change the dynamic link library without recompiling source code. And it says benefit, so we're not going to say that it runs slower, because if we say it runs slower, that's not going to be a benefit to the programmer whatsoever. And yep, that'll do it. So memory management is one of the tasks performed by an operating system. Describe the ways in which memory management organizes and allocates RAM. So RAM is organized into blocks of memory. So RAM is organized by a program into blocks of memory. And each program is going to reserve, a program reserves or allocates, we're going to say allocates RAM for the program. And what's great about RAM or memory management is that unused, or you can reuse RAM that is no longer being used because it stays on the RAM. So we can use those addresses because it stays on the RAM, and then when the program closes, we can reuse those parts that were already being used. And then one other thing we can write, and it's only asking for 2 things here. So we don't want to just keep writing. I'm trying to give you everything that you could use for this question. And it also will prevent multiple programs. So that would be 2 or more. It's going to prevent those multiple programs from using the same parts or addresses of the RAM. Because if I'm storing data on the RAM that I need for a program, I don't want it to be overwritten by another program. All right, let's just keep moving along here. So 7 points here for the operating system. May include a utility program to compress text files. Describe one appropriate method of compressing a text file. And this is important. When I compress a text file, that is definitely lossless compression. And there's one form of lossless compression, and that is run length encoding. Lossless compression by using run length encoding. Now, when I use run length encoding, I want to explain to my examiner what that means. And that means we look for repeating characters. So we replace repeating characters and what are we replacing them with? We're replacing repeating characters with a single character. Now, I don't want to say letter because it's not always just letters, but replace repeating characters with a single character and then how many times that character is used, followed by how many times it is used. All right. So I think that will be more than enough. Usually when they're going to ask you about run length encoding, they're going to give you a bitmap. They did not do that on this exam, and that's okay. Explain the reasons why increasing the amount of cache memory can improve the performance of a CPU. So cache is super fast memory. It's a lot faster than RAM. It is super fast memory, and the reason it's fast is because it is closer to the CPU. And the more, and it can hold repeatedly used instructions. That way we don't have to load it from the RAM each time. Can hold repeatedly used instructions, which is what helps make it fast. And you can increase it even more by having more registers. So more registers means more instructions that can be held. So it means more instructions. And we don't, the CPU isn't sitting idle waiting for the information to come in from the RAM. So lots of cache memory is great. State the name of a peripheral device port that provides a physical connection. How do we connect a 3D printer? USB. If you're unsure what to put, USB is probably the way to go. You can use USB. Something else you can use that is less common is a COM port. And then it says for a monitor, today that's mostly going to be HDMI. You may find some older cables that are going to use, or older monitors that use VGA. At our school, we have VGA. If you have a newer computer, you may also have a display port. That may happen, and you may have to get a USB to the display port, the DVI. Any of those will work. All right, let's go ahead and move on to number 8 and then number 9, and we'll be done. So I've learned a couple things while doing this video. One, it takes a heck of a lot longer to write out everything than it does to have it typed, and my handwriting did not improve as we move through this. But let's wrap up these questions. I've typed them out for you. A local area network uses bus topology. So this is something that was moved from A-level to AS a few years back. Describe how carrier sense multiple access collision detection is used in a bus network. So this is not asking us about terminators at all, but the CSMA-CD, it will prevent and detect collisions on the bus line. Now, here's what happens. A device will check to see if the line's currently being used. If it is being used, the device is going to wait for the line to become free, and then data is going to be sent. That is the preventing the collisions from happening. But if two computers or more than one device send something at the exact same time and may not notice that it is being used, and that's the collision detection. When a collision is detected, the transmission is aborted by each device, and each device waits a random amount of time before sending the data again. The reason it is a random amount of time is because it's highly unlikely that both the devices are going to choose the same random amount of time to wait. Let's move on to number 9, and let's wrap it up. These are the last questions on the exam. Many modern televisions are examples of embedded systems. Explain why these televisions are embedded systems. Because whatever device they're talking about, that system is built into the TV. It's not something that you have to attach to the TV. It's built into the TV, whatever that may be. Now, the owner, we cannot open it up and easily change out this system. The software and hardware, whatever it's being used for, it's being used to accomplish whatever task that may be. It says embedded systems use double EEPROM. So describe one benefit of using it. Well, we don't need any additional equipment to update whatever it is because it's updated through firmware updates. This means that electrically erasable programmable ROM can be used several times, and the reason it can be used several times because there are firmware updates coming out. Now, when the firmware updates the device, the device doesn't need to be removed. It can stay in the device and be reprogrammed or updated, which is the firmware update that is done in double EEPROM systems. Hope you guys found this video extremely helpful. If you did, please take a moment and give it a thumbs up and subscribe to help the channel grow. And we'll see you guys in the next review video.